An amplitude is a special type of azimuth type problem. Ultimately, what it is you're still just getting a bearing of the sun and calculating what its true bearing would be and comparing the two. What's special about these, though, is the amplitudes can only happen at sunset or sunrise. So when the sun is exactly on the celestial horizon, not the visible horizon. We'll get to that in a second. The celestial horizon, which is a little bit above the visible horizon. When the sun is in that location, or you can do an amplitude with the moon during moonset or moonrise, but we'll talk about that later too. That's a mess to deal with. But when it's, let's just say we're talking about the sun here, when it's exactly perfectly on your horizon, the math involved is a lot simpler. You can see it's literally just this equation here. The sine of the amplitude is equal to the sine of the declination over the cosine of the latitude. So all you need to find is declination and your latitude, and you can just instantly calculate the other, what the amplitude is. Now, it's also important to note it's called an amplitude and not an azimuth because those are two different things, obviously, but they're defined differently. Remember, if we draw a compass here, an azimuth is any bearing of a body that you measure as its deviation away from north or south. You know, we'll get like north 30 degrees east, north or north 20 degrees west, or south 20 degrees east, or whatever it might be. Either way, you take your default value here of either 0, 0, 0, or 180, and how far you're leaning away from that default value in either direction. And that's how you define your azimuth. That's why you have to do these z to zn problems here, where you're applying them. As you can see, you're applying them either to 360 or 180. An amplitude, I think you probably can assume where this is going, is a bearing of an object. Instead of being measured off of north-south, it's measured off of its deviation away from east or away from west. Obviously less common. It's not likely that you'd be doing something like this, but you're essentially saying how far away from due east or due west is this object. That's what this equation will give you. The number that it gives you will have to be applied to either 090 or 270 to get the true bearing of the object. These amplitude, like sunset corrections, are really the only time you would ever measure a bearing this way, which makes sense because, you know, it's sunset. It has to either be almost due east or almost due west in the first place. No other problem is really going to ask you to do this, but this is the type of correction we're dealing with here. There are some complications when we get to the the compass correction part, especially if you use the visible horizon, but let's look at the problem here. You can see in this situation, on 16th of April, we were in position 28 degrees so-and-so north, 81 degrees and whatever west, and we took a bearing of the sun. Now, notably, you could see the bearing was taken in PSC. I've never seen this before where somebody took a magnetic bearing of an amplitude. Doesn't really throw things off that much. We're just never going to have to do the GET portion. We're going to go straight to can Deadman vote twice. I haven't seen many questions that are like this. Normally they'll do the gyro corrections, not the magnetic corrections, but it's not hard to switch between the two. And then you can see it gave us our chronometer time and chronometer error. Notably, what it didn't give us was our zone time, what our local time was. And amplitude problems almost never do to mess with you, because if you think about it, you don't need that. You have your longitude, so you can find where your zone description is, so you could adjust your chronometer hours to whatever makes more sense in GMT. The only thing you really need the exact local time for is to tell whether it's sunset or sunrise. And you can see here, if the sun was bearing 70 degrees per standard, it's probably sunrise, right? It's not, it's in the east of you. It has to be sunrise. It can't be anything else. So you now know you're in the morning, and you now have a better idea of how you can correct the chronometer time here. So we're going to start from the top. Because we don't have zone time, we'll just do zone description, and chronometer time, chronometer error, and GMT. So zone description, we're in 81 west. So 81 is almost 90, so that should be plus 6. 81 divided by 15 is 5.4. Okay, well, we'll do 47 divided by 60 plus 81 divided by 15 is 5.45. Okay, so it actually rounds down to 5. So we'll do ZD plus 5. Now our chronometer time is 10, 53, 41. And we got a chronometer error of 2 minutes, 23 seconds low again. So now our GMT, 41 plus 23 is going to be 04. Carry the 1. 54 plus 2 is 56. Now, for our hours, it's either 10 or it's 22 because we're, that it's 12-hour time. It's going to either show 10 a.m. or 10 p.m. But we know if we're in the west, and it's sunrise in the west, it's probably like 0600 realistically, meaning if it's later in the day for Greenwich, because we're west of them, so it's we're later, or they're later than us, their clocks show, then that 0600 for us plus 5 would get us to right around 10, so we can assume that this GMT hours is 10 as well. So now we've got our GMT time of 10:56:04. And we're going to open the book to 16th of April. There we go. And we're going to come to the sun side. And remember, this equation only needs latitude and declination. So the only value we're going to look for here is our declination. So we're coming to the 16th at 1000. We had a declination of north 10 degrees and 9.6 minutes. So we'll just write dec north 10 degrees, 9.6 minutes. And we had a little d value of 0.9. It's April. Before the solstice, so this should be increasing, and if you look, they are going up, so it's plus 0.9. So now we're going to come to the increments and corrections. There. And we are looking for 5604. So there's 40, 56, and 0.9 in the d value is 0.8. So this is equal to positive 0.8. So then we're going to add the two together, and we'll get north 10 degrees 10.4 minutes. Okay, there's our declination right there. Now what we can do is we can actually apply all of this to our equation. So our equation is sine of A, our amplitude, is equal to the sine of the declination divided by the cosine of the latitude. So we'll just carry over these values. The sine of our amplitude is equal to the sine of 10 degrees, 10.4 minutes. And the cosine of our latitude is up here, 28 degrees, 07.0 minutes north. Now it's important to note, just like when we're using any other equation where we're working with latitudes and declinations, If they were contrary, you would have to give negative values. You'd have to set one of them as negative. But in this case, let's see, would it matter? Yeah, I think it would matter. I think you should set the declination as negative. But in this case, they're both north, so they can stay positive. And now we'll just run the calculations. So let's see. 10.4 divided by 60 plus 10. Then we'll take sine of that, and that gives us the numerator. Then 7 divided by 60 plus 28. We'll take the cosine of that. That'll give us our denominator. So we'll divide the 2. Sine inverse of the answer. We'll get 11.55. So A here is equal to 11.55 degrees. Now, if this was an azimuth, when we got our Z, technically we should label it as Z, like north, however many degrees east, just like we do our course angle in Mercator sailings or Great Circle sailings or whatever we might be working on. But this is an amplitude. Those things are all technically azimuths, which is why they're usually written as Z or Zn. So in an amplitude, we'd actually write it the opposite way. We would put the east-west first and the north-south second to show that it's 11.5 degrees north or south of due east or due west, as opposed to 11.5 degrees east or west of due east, due north, due south. So let's see. It's sunrise, meaning we know that the bearing is to the east. We don't need to check anything specific. We just know that if it's sunrise, it's in the east. And for the north-south value, the value we're actually going to use is drawn from the declination. So whatever the declination is, we throw that on to the north-south here. Meaning if the declination in this problem were south, we would write east 11.5 degrees south. But because it's north, we wrote east 11.5 degrees north. So now we can draw our little diagram again of an amplitude. West. So we know here that we're in the east and we're 11.5 degrees north. So we're going to use this. And I don't think I even needed to draw it out, but to actually calculate what the true bearing would be, in this quadrant we would do 90 minus amplitude. In this quadrant we'd do 90 plus amplitude. This would be 270 minus amplitude, 270 plus amplitude, which is obvious. You can see that's exactly what these diagrams are showing. If we're in the north, if it's east and north, we're going to go up from east, which is subtracting. So we're going to do 90 degrees minus 11.55 degrees. 90 minus answer gets us 78. Zn is, or not, sorry, true bearing. So yeah, I guess I'll just write bearing, because it's like Zn would not be technically correct. Just the true bearing of the body of the sun here is 078.4 degrees. Now, one thing I forgot to write in the problem here is that we used the visible horizon for this problem. Remember, when you look out at the sky, here you are, looking straight up gives you your zenith. And then the horizon is defined off of your zenith as just, the horizon is defined off of your zenith as just 90 degrees away from your zenith in all directions. So this is the celestial horizon. This is kind of hard to show because it's right at the bottom of the page. However, because you're not just like a point on the surface of the earth, you have height and on the bridge of a ship, you probably have a good like 50 to 80 feet of height. You can see past perfectly 90 degrees. Your field of view goes in both directions a little bit further. You can see up to like probably 100 degrees, 110 degrees, just about. It's not easy to show because I made this diagram too big, but if we come over to this page and we draw it like this, that would be the celestial horizon right there, but you can see down to here. And what that means is that if you took a shot of the sun when it hit the visible horizon, when you actually saw it touch the water, that would be it at the visible horizon. But these calculations only work for the celestial horizon. The rule of thumb is the celestial horizon is when the sun's lower limb is about 2/3 of its total height above the water. So if this is the horizon, the sun being on the celestial horizon would look like this. It's when it's exactly halfway on. You wouldn't want to look for its lower limb. You'd want it, everything's defined off of its center. But the celestial horizon is somewhere up here. So if the sun were on the celestial horizon, it would be like this. What that means, though, realistically, is you could fit another just about 2/3 of the sun underneath itself and have that hit the visible horizon. So when the sun looks like this, when it's really like almost at sunset, but it's still got a 2/3 of its width, or usually you could say a pencil width or like a finger's width above the horizon, that's when it hits the celestial horizon. And that's a little more difficult to do, but it's a lot easier when it comes to the math. So whenever you take an amplitude of the sun, you want to take the celestial horizon. In this problem, we took the visible horizon. And what that means is we're going to have to apply a correction that, I forget, is it in the almanac or is it in Bowditch? Let me see. I think it might be in Bowditch. Yeah, it is. Let me grab Bowditch. I'll be back in a second. Okay. Now bear with me for a second because I don't remember exactly what page of Bowditch it's on. So we're going to come to the contents here. Navigation tables, it should be around here. Okay, here. Next page over. You can see right here, table 22 amplitudes. So this is what we're going to need. Page 698. Oh, wait, no, this is the wrong one. Sorry, this is actually, if you didn't want to do the equation, you could just find your amplitude values right from there, because this is not showing us our horizons, which is what I want. Yeah, it was the page right before it, or right after it, table 23, corrections to between the visible and I said 693, right? What's table 23 then, if I remember? Okay, here we go. Correction of amplitude as observed on the visible horizon. You can see right here, we have columns defined by declination, rows defined by latitude, and at the bottom, it'll explain for the sun, planet, or a star, apply the correction to the observed amplitude in a direction away from the elevated pole. For the moon, apply half the correction towards the elevated pole. What they're saying there, because I know that's kind of confusing, is I'll open to a new page because this is going to take a little bit of room to explain. But if you think about the sun, let's say we're in the north. Here's our position. And the sun comes in at sunrise at about 090, bearing generally due east of us. If we're in the north, you know, obviously it's going to set in the west, but it's going to travel this way to take that path because the sun is south of us, which is why at noon the sun will bear exactly 180, and at sunset it will bear something around 270. If we were in the south, it would head this way because the sun is north of us, so its bearing would swing up the compass and around that way as opposed to down the compass and around that way. So at any point throughout the day, the sun is somewhere in the north, somewhere southerly of you, and this is the path that its bearings take as you watch it go throughout the day. Because the visible horizon involves the sun being a little bit further, like it is past the horizon, and the horizon is a little bit above. You know, here's the visible horizon, here's the celestial horizon. What that means is that if you measured the sun out at its celestial horizon, that's when it's exactly correct. If you measure the sun at the visible horizon, when it's a little bit closer to being obscured, in the morning, that means the sun was either up here, or in the evening, it means the sun is over here. Because in the morning, for it to be closer down and not as high up in the sky, that meant that it was a little further back in its path, so it happened a little bit earlier. And then in the evening, for it to be a little bit lower in the sky, that means it happened a little bit after the sun was at the celestial horizon. So, if you measured the sun here instead of here, you would need to correct your shot from when it bore this to when it now would bear this. So your correction would be applied this way. If it's sunset, you would have to apply it this way. Now what you can notice is this is only true if we're in the north. And in the north, the correction is always going towards the south. If we were in the south, then the bearing would have been, remember, because in the south, the sun takes a northerly path, so the bearing would have been, to be on the visible horizon, would have been down here, so then it would have to apply upwards. Meaning, if you were in the south, the correction would have to be to the north on either side. What this is telling you is the same as what it says in the table here. For the sun, planet, or star, you apply the correction away from the elevated pole. So if you're in the north, north is your elevated pole, so you go south. If you're in the south, south is your elevated pole, so you go north. And you apply the correction to the observed amplitude. The observed amplitude being the one you actually measured. Because remember, this is wrong, this is correct. This is what you actually shot. This is what you calculated. So you have to take what you actually shot and apply that correction to get it closer to what you calculated. If we look back at here, in our problem, we got a true bearing of the sun of 078.4 degrees. But that was when the sun was on the visible horizon. So if we're in the north when this happens, we're going to have to go into that table, find a correction factor, and apply it to the south. And if the sun is bearing this way, then to the south would mean we add it. So we're going to have to add this correction value. Now, if we were in the south, then we would have to subtract it. And if it was sunset, then we would be applying all of this to 270, and then it would be adding and subtracting flipped. So always draw it out so you don't confuse yourself. Just know that you're applying it away from the elevated pole. So now we're going to do our calculation. And let's see. First we look for our declination. And our declination in this problem was 10 degrees. Approximately 10 degrees, but it's this is all approximate. And our latitude was 28 degrees. So we're going to follow this table down until we get to 28, which our closest value is 30. So we're going to take 10 degrees and 30 degrees, and we get 0.4 as our correction. So our correction is 0.4 degrees. And we know, based on what we just figured out, because we're in the north, therefore the sun was somewhere up here, that correction is going to be added, not subtracted. So we plus 0.4, and we're going to apply that not to our true bearing, because our true bearing is correct. We apply that to the bearing we got off of the compass itself. So our compass bearing was 073.5 degrees. I actually failed near coastal on my first attempt during license because I forgot to apply the amplitude correction to the observed bearing, not the true bearing. I passed on the second attempt. So we're going to add these two together, and we'll get 073.9 degrees. And now we can actually do our compass correction, because now we have our true bearing and the bearing of the sun when it was at, that we measured when it was at the celestial horizon. Doesn't matter what the visible horizon was doing. We want to know where it was at the celestial horizon. So we can draw, can dead men vote twice at elections? And you'll see our compass bearing was 073.9 degrees, and our true bearing was 078.4 degrees, and our variation was 11 degrees east. Okay, so we're going this way to get from true to magnetic. So this way, east is subtract, so we would get 067.4 degrees. And now we can compare the two, 067 to, that's the calculator. All right, there's the calculator. 73.9 minus 67.4 gets us 6.5 degrees. So 6.5 degrees is our deviation. Decreasing going this way, so it's west. So our answer would be our deviation is 6.5 degrees west. To review, when you get an amplitude, the only thing you need to find out of the book is declination. And then you just real quick perform this formula here, sine of declination over cosine of latitude. That will give us our A value. You have to then remember whether your A value is affected by east or west. If it's sunrise, then it's east. If it's sunset, it's west. And then whether you're going north or south is based off of the sign of your declination. The declination is in the north, then we're going to do north. And so in this case, we had east and north, meaning we would subtract A from 90, and that would get us our true bearing of the sun. And then if we had measured the sun on the celestial horizon, that's all the work we'd need to do, and we could go straight to can dead men vote twice. But if we measured it on the visible horizon, then we need an additional correction. this correction is going to be applied to our bearing, not the thing we calculated, but the thing we actually measured off of the alidade. So then we got to remember that when we look into this correction, which is based off of the declination and the latitude, it's going to be some small change in bearing. And we're going to apply that value in the opposite direction of the elevated pole. So if we were in the north, then this was the sun at the visible horizon, and this was the sun at the celestial horizon. So to get to the celestial, we'd have to apply it away from north. If we were in the south, then this would be the visible horizon. We'd have to apply it away from south. So in other words, at sunrise in the north, we'd be adding, and at sunset in the north, we'd be subtracting, and vice versa for the south. So we get that correction factor. We apply it to our original measured bearing, and we would get the true bearing of this, or the bearing off of our compass of the sun at the celestial horizon. And then from there, we could compare the two and get our deviation. Now, as you saw, there's some special stuff for the moon. We're going to do that next. That is a whole mess, but technically the one I got wrong on license was a moon problem, making it even harder. Just hope you don't get those. They suck.